Hello everyone, welcome to another particular lecture of our Stereochemistry course. And in this particular lecture, we are talking about the topicity of organic compound. And topicity of organic compound is a very important chapter in terms of exam point of view, because in every year there is a one question is there from topicity. So in this particular lecture, we are talking topicity in brief. Okay. So first of all, what is topicity? Topicity refers to the relationship and the spatial orientation of identical or similar group of atom in a particular molecule. Okay. And there is a three type of topicity that are the point of interest. There is a homotopic, enantiotopic, and diastereotopic. So we are looking onto that particular topic. Okay. So first is called the homotopic. Homotopic is identical group or atom that are indistinguishable, that is very important, indistinguishable in all respects, including their chemical environment and reactivity. Okay. And replacement of either group by a different substrate give the same product. So what happened that in exam point of view, there is a questions like this type of question, and between this H1 and H2, you have to determine the relationship, like either this are homotopic or not. So there is a two type of thing that anyone can do to determine the topicity. So the simple thing, and that is the important thing, is the addition elimination criteria. So we just change this particular one group to different substituents. So here I am changing H1 with Br. So we got this particular group. Okay. Similarly, if we change H2 with Br by some kind of hypothetical reaction or some kind of a reaction. Okay. So if we got this. Now, interestingly, if we see that both are the same product, like if we rotate this particular molecule by C2, then we can found that both are the same. So that means that H1 and H2 are homotopic in nature. So here we can say an interesting thing, like by method we are determining the relationship between two hydrogen are homotopic or not. So like first in the addition elimination criteria, first you have to change, okay, one substituent with other different groups and see that whether the particular molecule is chiral or not. So interesting, this is a not chiral molecule. Similarly, if we change this particular group, this is also not chiral. So they are homotopic in nature. Also in symmetry point of view, if the molecule contains Cn, N should be anything present, then the molecule must be homotopic in nature. Okay. Next is the enantiotopic. Enantiotopic says group or atom that when replaced by a different substituent produce enantiomer, that is non-superimposable mirror image relationship, and found in chiral environment and affect the optical activity. Obviously, since it is a forming enantiomer, it should affect the optical activity. Example, we can take this particular compound, this is the ethyl benzene. Now we have to determine the relationship between these two particular groups. So first we are doing our addition elimination criteria. First we are change the HB with Br. So what we have found? We have found that this particular center now become a chiral. Okay, and this is a R1 bromoethyl benzene. Similarly, if we change HA, okay, HA with Br, then we can found that the stereochemistry is again changed. Initially it will be an R, okay, it will be a R, and now it will be a S. So that means these two are nothing but enantiomers to each other, like they are non-superimposable mirror image. That means HA and HB are enantiotopic in nature. Now interestingly, we can see that it is a prochiral center. This carbon is a prochiral center because changing on one group will lead to a enantiomers. That means a chiral center. So we can say that if there will be any prochiral center is there, then prochiral center groups are enantiotopic each other. Also, another very interesting observation from here, since we change HB to Br to get this particular chiral center as R, that means we can say the HB is pro R center, like changing HB will generate R enantiomer. So HB will be pro R. Similarly, if we interchange HA to other compound or other molecules, then we get S. That means HA is classified as pro S center, like it is not R or S right now, but after changing substituent we can say that this particular HA will be pro S and HB will be pro R, and this type of question will come in the exams, so be cautious about that. So we are very much clear about the enantiotopic right away. Now we are talking about diastereotopicity. Diastereotopicity says group or atom that when replaced by a different substituent produce diastereomers. And this group of different chemical environment may have different reactivity. Obviously, diastereomers have different chemical and physical properties, so it will obviously show different reactivities. Example, see here, this is also already a chiral center present, and adjacent center here coming the two hydrogen. If we do our addition elimination criteria, then we can found that this will become another center, that is a chiral center. So S2 methyl butyne benzene, now changing this particular H, okay, by changing this particular H, okay, now changing this particular H to Br, we are generating this particular compound where is the R and this is the S. So 1R 2S 1 bromo 2 methyl benzene, and if we change this particular hydrogen, the wedge bond hydrogen with Br, then we are getting 1S 2S 1 bromo 2 methyl benzene. That means these two doesn't have any mirror image relationship, no symmetry present. That means these two are diastereotopic in nature. That means these two hydrogen are diastereotopic in nature. Okay, so the easiest way to remember diastereotopicity is the molecule should have an existing chiral center, and there will be a group that we have to determine that whether the compound these are diastereotopic in nature. That means if any compound contains already a chiral center, okay, then we can, then the particular center, the adjacent, if there is a two different group is similar group is there, then we can say these two are diastereotopic in nature. So it is a simple easy observation, not easy, like we can say that it is a crucial observation that actually saves time in your exam hall. Okay, now there is the summary. Let us talk about the summary of the particular topic relationship. Like if homotopic, then after doing substitution or addition criteria, we got the identical product. And what is the symmetry? That the particular ligand, that is the two hydrogen, can relate it through the CN axis or C2 axis. And difference, there will be no difference. Since the identical product we have observed, so there will be no difference at all. In enantiotopic case, after substitution addition criteria, we got enantiomers or enantiometric product. And also the symmetry, like if the particular ligand are facing to ISN or sometimes plane of symmetry, that is sigma, then we can say that that particular the ligands are enantiotopic in nature. And how do we distinguish? Like simply enantiomer, how do we distinguish? By using NMR or chiral reagent or the chiral HPLC, we can distinguish the two particular compound. And diastereotopic, it will generate diastereomers after addition substitution method, and the ligand and phase not related by any kind of symmetry element and no mirror image relationship at all. And how it is distinguished? It is distinguished by all methods since they are the two different compounds. Okay, now let us talking about the ligand topicity. First is the homomorphic ligand. Homomorphic ligand as those ligand which are generated having a homotopic relationship. Okay, so homomorphic ligand, if there is a symmetry element related, then it is a homotopic. If no, then it is a heterotopic relationship. Okay, like, and if it is attached to constitutively equivalent center, then it is a stereoheterotopic ligand. And if it is a symmetry element of second kind, that is the sigma ISN. If yes, then it is called the enantiotopic ligand, and if it's no, then it is a diastereotopic ligand. And the symmetry element of first kind, it is suggests PL. Okay, so this is the broader classification of ligand topicity. So I hope this will be clear. So in this particular lecture, we are talking about the topicity, like enantiotopic, diastereotopic, and the homotopic ligand. We are already discussed about the symmetry addition elimination criteria, as well as the symmetry criteria to determine the enantiotopic, diastereotopicity, and homotopicity of the particular ligand. And we are also talking about the ligand phases, homomorphic, enantiotopic ligands, and diastereotopic ligands in brief. So with this, we have to end this particular lecture, and in the next lecture, we are talking about the optical activity. And optical activity in this particular lecture, we are talking about that how chiral molecule can rotate plane polarized light, and we are talking about some different terms, that is specific rotation, optical rotation, and enantiometric axis, diastereometric axis. So be with this, wait for the particular lecture. And till now, we have to revise whatever we have learned. So please do revision properly. So with this, we have to end this particular lecture. We'll meet on next lecture. That is lecture 12, optical activity. So thank you for listening.